All right, hello everyone, and welcome to tonight's astronomy talk. Last week we talked a lot about the terrestrial world's surface features and interiors. Tonight we're going to focus on the atmospheres that surround those worlds. But just like last week, there's so much material to talk about that there will not be any of those little multiple choice questions here either. So comment down below or direct message me if you have any questions. I would be more than happy to help you understand something. Tonight's quote comes from the German astronomer Ulf Merbold. His comments when he left the bounds of Earth for the first time. He says, "For the first time in my life, I saw the horizon as a curved line. It was accentuated by a thin seam of dark blue light, our atmosphere. Obviously, this was not the ocean of air I had been told it was so many times in my life. I was terrified by its fragile appearance." All right, so here's a table full of information on all the atmospheres of the terrestrial world, including our moon. And you can see a wide variety of features. So Mercury and the moon have so little atmosphere that we essentially just call them airless. They don't have winds, they don't have weather, hardly anything to speak of. On the other extreme, Venus has such a dense carbon dioxide rich atmosphere that it makes the surface conditions very hellish, 470 degrees Celsius on the surface, with sulfuric acid clouds. This is so dangerous that not even our robotic spacecraft can survive on the surface of Venus for very long. Meanwhile, on Mars, it also has a carbon dioxide rich atmosphere, but it is such low pressure, about 7,000th times the surface pressure of Earth, that you would need a pressurized spacesuit to walk around on Mars. Earth is the only planet, it's in the Goldilocks zone. It has the just right conditions for liquid water to exist on the surface and for life to eventually arise. But despite this wide variety of conditions on these planets, on these worlds, we can understand it's the same atmospheric processes that happen on all of these. And we can understand it by first talking about the general properties of an atmosphere. So an atmosphere is generally characterized by its atmospheric pressure. What is this atmospheric pressure? Well, the pressure is caused by the collisions of individual atoms or molecules. Now, on Earth, the nitrogen and oxygen molecules fly around in the air on average at speeds of around 500 meters per second, which is fast enough to cross your bedroom 100 times in 1 second. On average, each molecule in the air around you will suffer 1 million collisions in the time it takes me to get through this sentence. And these collisions are the things that are creating the pressure that pushes in all directions, and this pressure holds up the atmosphere so it doesn't collapse under its own weight. But gas in an atmosphere is held down by gravity, which compresses the atmosphere by some amount at any altitude. But at the same time, molecules will exert pressure in all directions, which makes the atmosphere at any altitude expand. So an atmosphere is always in this sort of perpetual state of balance between the downward weight of the gas caused by gravity and the upward push of all that gas pressure. So the higher you go in an atmosphere, the less weight of the gas above you, which means less pressure, which is why the air pressure decreases as you climb a mountain. You can sort of visualize this by this little pillow analogy we got going on here. The pillows at the bottom are very highly compressed because of the weight of all of the pillows on top. And going upward, the pillows are less and less compressed because less weight lies on top of them. In planetary science, we generally measure atmospheric pressure in terms of bars, where 1 bar is equivalent to about 1 kilogram per square centimeter, or 14.7 pounds per square inch. Essentially, the surface pressure on Earth. So Earth has a surface pressure of 1 bar. However, at some point, that density of gas is so low that we can't really talk about it as if it's air. There's really nothing there for air to be. If we were to go up so high in the Earth's atmosphere, where the density is very low, we wouldn't be able to breathe, even though there is technically still air up there. It's just because the collisions between the molecules are rare at those levels. On the Earth, this happens at an altitude of about 100 kilometers or 62 miles up, and that's what we generally define as the edge of space. By the way, that 14.7 pounds per square inch of atmospheric pressure, that sounds like a lot. If I push down on your shoulders with nearly 15 pounds per square inch, so about that big, on your shoulders, you definitely feel it. So why don't we feel that 14.7 psi, pounds per square inch? And that is because, first of all, that pressure pushes in all directions. So it pushes upward and inward as well as downward on you, pushes all directions. And second, the fluids in your body also push outwards with an equal pressure. So there's no net pressure trying to compress you. Our bodies are made to withstand 14.7 psi. So you don't have to worry about that. Our bodies we've evolutionary adapted to that amount of pressure. That's why we don't feel it. All right, so atmospheres are obviously very important to our existence, particularly here on Earth, but the full range of atmospheric effects is usually wider than most people believe. So here's a few key effects. So atmospheres create the pressure that determines whether liquid water can exist on the surface. Mars, as we'll find out, has such low pressure that no liquid water can exist on the surface. Atmospheres also absorb and scatter light, which makes the daytime bright, which is why we could see outside during the day, but it also prevents dangerous radiation from reaching the ground. Atmospheres can also create wind and weather and play a role in this kind of long-term climate change. Interactions between the atmosphere and solar wind can create a protective magnetosphere around planets. We kind of talked about that last week. And then atmospheres can also make planetary surfaces warmer than they would be otherwise via the greenhouse effect. And that's what the last point is what we're going to start tonight with. Now, you probably heard about the greenhouse effect through its role in the problem known as global warming. But the greenhouse effect in and of itself is not a problem. In fact, it's what makes Earth livable today. So let's talk about that. How does the greenhouse effect work? So obviously the sun is emitting primarily visible light. We talked about that many weeks ago. The sun is at right temperature to emit most of its light in the visible range of the spectrum. And so as that visible light enters the atmosphere, some of it is just going to be naturally reflected into space. The Earth is a little bit reflective. We've got ices, we've got water on here that is very reflective and will bounce some of that radiation back into space. But most of that visible light is absorbed by the planet. Now, the planet, unlike the sun, is at a temperature where most of its light is going to be radiated in the infrared. So the planet is going to take the sun's visible light, absorb it, and then re-radiate that in the infrared. And that infrared light is key to the greenhouse effect because certain molecules, which we call greenhouse gases, like water vapor, carbon dioxide, and methane, they absorb infrared light and slow that escape of infrared light or heat from the planet. Now, a greenhouse gas molecule does not keep a hold of this infrared energy forever. It will spontaneously re-radiate away in a different direction. So infrared light sort of just bounces around in the atmosphere, sometimes going up and then sometimes coming back down, sometimes going sideways, sometimes, eventually it will leave the planet, because the greenhouse effect doesn't actually alter a planet's overall energy balance. The total amount of energy that a planet receives from the sun is very much balanced with the amount of energy it returns to space through reflection and radiation. Otherwise, the planet would rapidly heat up or rapidly cool down. So all the energy trapped by greenhouse gases does actually eventually escape to space, just not as directly as it would otherwise happen. You can think of it sort of like Earth's blanket. You stay warmer underneath a blanket, not because the blanket itself provides heat, unless you're like me and you have an electric blanket that you love very much, Normal blankets don't heat yourself up because they're doing all the heating. They're doing it because it slows the escape of your body heat into the cold outside air. So the greenhouse effect is like a planet's blanket. Eventually the heat will get out, but it slows that process down. Now remember, we can really appreciate the importance of the greenhouse effect by comparing each planet's average surface temperature, the global average surface temperature, with and without it. So remember that sunlight is the only significant energy source for the surface. The surface is not heated hardly at all by all those internal processes we talked about last week. So without the greenhouse effect, a planet's global average temperature would depend only on the distance from the sun and the planet's overall reflectivity. So here's a table full of information on all of the terrestrial worlds. So you see their average distances, obviously increasing from Mercury and Mars. Reflectivity, Venus is the most reflective planet. The Moon and Mercury are the least reflective. And then that third column is their no greenhouse average temperature. So if they did not have a greenhouse effect, how cold or hot would those planets be? So Mercury would be very hot because it's very close to the sun. And not that much reflective. So it's going to absorb most of the heat that the sun is giving it. So surface temperatures of 163 degrees Celsius. Meanwhile, Venus, way below freezing, minus 40 degrees Celsius. Earth, definitely below freezing without a greenhouse effect, minus 16 degrees Celsius. The moon, much warmer because it has less reflectivity. So it's going to absorb all that heat. And then Mars, minus 56, the coldest planet because it's far out from the sun. If we look at what their actual recorded average temperatures are, first of all, we see that the Mercury Moon, their no greenhouse average temperature is in between their day and night temperatures, which makes sense. The Mercury and the Moon don't have an atmosphere to have a greenhouse effect, so we're okay with that. Venus's actual average temperature is much, much, much higher than its no greenhouse average temperature. So with the greenhouse effect, Venus has been warmed by over 500 degrees Celsius. Mars, remember, even though it has an atmosphere primarily of a greenhouse gas, carbon dioxide, it's such a thin atmosphere that it warms very little, by only about 6 degrees Celsius. The Earth, despite the fact that water vapor and carbon dioxide and methane make up an insanely tiny fraction of the molecules in the Earth's atmosphere, thanks to that greenhouse effect, it's been warmed by 31 degrees Celsius. So instead of being below freezing, we're above freezing. And so liquid water can exist on the surface. So the greenhouse effect is not at all completely bad. Without it, we certainly would not be around here to appreciate it. We need the greenhouse effect. The problem with the greenhouse effect is when we start messing with it. And we'll talk about that towards the end. All right. Atmospheres also vary with altitude. Their properties vary with altitude. So this is a model of the Earth's atmosphere. So on the vertical axis on the left, you can see the altitude in kilometers. On the horizontal axis towards the left, you can see the temperature. So left is very cold, right is very hot. Excuse me. And this red squiggly line here traces out how the temperature changes as we move upwards in altitude. So we'll start at the bottom. The bottom is called the troposphere. This is the lowest layer where the temperature drops with altitude. The higher you go up, the colder it's going to get. Then, as we move into the next layer, the stratosphere, the temperature starts to rise again with altitude, but then falls again higher up. Then we enter the thermosphere, where the temperature starts to rise drastically again. And then the exosphere, where the atmosphere just sort of fades away into space. Now, the key to understanding why we have these different structures and why the temperature is changing so weirdly through the atmosphere as we vary with altitude comes from the interaction of the sun's light with the gases in the atmosphere. So You can see on the right side of this diagram different types of light: X-ray, UV, visible, all the way down here at the bottom we got infrared. So X-rays have enough energy to completely ionize almost any atom or molecule. So they're absorbed by virtually all the atmospheric gases and don't make it very deep. That means they also sort of heat up the top layers of the atmosphere. UV photons will break molecules apart, such as water and ozone. Ozone is three oxygen atoms weakly bonded together, so it's very readily broken up by ultraviolet light. Visible light passes through atmospheric gases without being absorbed, although they can be scattered. And then infrared light, as we just talked about, is absorbed by greenhouse gases. So let's look at these different lights and their interactions with our atmosphere in more detail. So when it comes to visible light, scattering of visible light makes the daytime sky bright. Without it, light would just travel in straight lines, and we would just see the sun against a backdrop of black. It would be like whenever I show people planetarium software and I turn off the atmosphere. That's what happens. The sky goes black. You can see all the stars. The sun is just bright against that backdrop of black. But that scattering also explains why the sky is blue. So gas molecules scatter blue light because blue light has higher energy, and they scatter more effectively than red light, which is lower energy. And so the blue light reaches our eyes from all directions. It doesn't just come straight from the sun. But at sunrise or sunset, the light has to pass through a lot more atmosphere. It's going like on the edge of the Earth. So all of that blue light is scattered away, which results in those orange-red skies. By the way, the reason, very commonly, as you can see here in this XKCD comic, you tell a kid this, and they'll ask, why isn't it violet? Because purple light is even higher energy than blue light. The reason our sky isn't purple is because, first of all, the sun does not emit a lot of light in the purple side of light. That gets too close to the ultraviolet, and the sun doesn't emit a lot of ultraviolet light. And secondly, our eyes are just not adapted to absorbing purple, violet light as opposed to blue, green, and red. So there's a physical and an evolutionary reason why our sky does not appear purple, instead appears blue. Now, when it comes to ultraviolet light, that is the primary source of heating in the stratosphere. That is why the heat begins to rise as we go up the altitude, because ozone absorbs UV light. And this happens pretty high up, around 40, 50, 60 kilometers up, which is why the temperature increases with altitude. That temperature structure, where we've got hot and then cold, also prevents convection from happening. So in the stratosphere, there's no weather. There's no movement happening there. So that means pollutants like chlorofluorocarbons, CFCs, that was big in the news a few decades ago. Those remain there for decades. So that's why we stopped putting CFCs in our hairspray and our insecticides, pesticides. We stopped putting CFCs in those because they were degrading the ozone. Now, a very important point here is that a planet can only have a stratosphere if it has molecules that absorb UV. Since the other planets don't have oxygen in their atmosphere, they're primarily carbon dioxide, Venus and Mars, they won't have ozone. So the Earth is the only terrestrial planet with a stratosphere. And when it comes to X-rays, X-rays pass through the exosphere very easily because there's so little gas up there. The density is so low that they're not going to hit a molecule up there. So they usually make it into the thermosphere before being absorbed, the mesosphere sometimes called. That absorption will heat the gas in the thermosphere, but it's really of too low density for it to be felt. Remember, this is sort of the difference, once again, between temperature and thermal energy, where thermal energy depends on the density of those molecules. However, a small portion of the thermosphere does contain gases ionized by X-rays, and so we call that portion, the ionosphere, which is very useful for radio communication since radio waves bounce off the ionosphere and allow radio to circle the globe. Without that reflection, radio communication would only work between locations in line of sight to one another. So it's very useful for things like these little Zoom lectures. And when we compare atmospheres, so the moon and Mercury are left off here because they have so little gas. They really only have an exosphere. But Venus, Earth, and Mars are put on this plot. Here we've got temperature in degrees Celsius on the bottom horizontal, altitude in kilometers on the vertical, and temperature in kelvins on the top horizontal. And you can see that Venus, Earth, and Mars all have a troposphere down here, which is warmed by the greenhouse effect, and a thermosphere up here, which is heated by X-rays. But only the Earth has this little bump out, which is indicative of a stratosphere, because, like I said before, the Earth is the only thing with such a easily ultraviolet absorbing molecule like ozone. These arrows are what the planet's surface temperature would be if there was no greenhouse effect. So you can see everyone is slightly warmed, especially Venus. All right, so how do atmospheres create wind and weather? Now, just to clarify, weather refers to the combination of winds, clouds, temperature, and pressure that makes some days hotter or cooler, clearer or cloudier, or calmer or stormier than others. Climate is the average weather over many, many years. So, for example, we say that Antarctic deserts have a cold, dry climate, even though it sometimes might rain or snow. So that's the difference between climate and weather. We're going to talk about weather first. We'll get to climate towards the end. So here on the Earth, we're going to talk about primarily the Earth here for a little bit. The wind direction and strength changes rapidly from place to place, but there is obviously a general global wind pattern that varies with latitude. So you can see up here at the top right, we've got different winds. So equatorial winds blow from east to west. Mid-latitude winds blow from west-east, and high-latitude winds blow like equatorial winds from east to west. This is why if you've ever been bored one day and watched the Weather Channel and looked at the radar as storms move across the United States is mostly in the mid-latitudes. And so you'll see lines of storms move mostly from west to east. And that's because they're following the general global wind pattern for mid-latitude regions. That's why it happens. Now, why do we have these different global wind patterns? Well, one of the reasons is because of atmospheric heating. This is partly to blame since the equator receives more heat from the poles. So warm equatorial air therefore rises upward and flows towards the poles, where cool air descends and then flows towards the equator. So if the Earth had no rotation, then we would have two large circulation cells, otherwise called Hadley cells, where you can see here, warm air from the equator would travel to the poles, cold air from the poles travels to the equator. And this has the effect of making the poles slightly warmer than they would be otherwise, and the equator slightly cooler than it would be otherwise. Circulation cells happen on Venus and Mars too. However, on Venus, the circulation cells transport thermal energy so effectively that the entire planet is the same temperature. On Mars, the atmosphere is so thin that very little thermal energy is transported, so the poles are much colder than the equator. So very, very important. Now, obviously, planets rotate, so we don't have just two large circulation cells. What comes into play is something you probably all heard about, the Coriolis effect. This effect causes equatorial regions to circle around Earth's axis faster than polar regions. So air moving away from the equator has some sort of extra speed that causes it to move ahead of Earth's rotation to the east, while air moving towards the equator lags behind Earth's rotation to the west. In either case, moving air turns to the right in the northern hemisphere and to the left in the southern hemisphere. So, for example, this hurricane, if it was moving to the west, it would curve upwards. This hurricane, the southern hemisphere, if it was moving towards the west, it would curve downwards. This also has the effect of determining what directions hurricanes rotate in each hemisphere. So this is a time-lapse images of one particular hurricane, Hurricane Dorian, I think. And it was in the northern hemisphere. You can see it rotating counterclockwise. Hurricanes in the southern hemisphere will rotate clockwise. Now, this only happens for these storms that are hurricanes move across the planet. They change latitudes. They do actually change latitudes, as opposed to like tornadoes that generally stick in one region. So the Coriolis effect doesn't actually affect what way a tornado rotates, or even that common myth about toilet spinning different directions in the northern and southern hemispheres has nothing to do with it. It's too small of a force for tornadoes or toilet bowls to actually exhibit. So what does the Coriolis effect mean for our two big circulation cells? Well, it actually splits them into three smaller circulation cells. So as the Earth rotates, and remember, air from the North Pole wants to go to the equator. But the air from the North Pole gets diverted towards the west well before it reaches the equator, which forces the large circulation cell to split into three smaller circulation cells. And these smaller cells act like gears, diverting winds near the equator and poles westward, and winds and mid-latitudes eastward, which is why those global wind patterns are the way they are. Earth is the only terrestrial world with a strong Coriolis effect, because the Coriolis effect depends on the planet's size and rotation rate. So the larger you are and the faster you rotate, give you a stronger Coriolis effect. So Venus has a small effect because it has a very slow rotation. Remember, it takes 243 days for it to rotate on its axis. Mars has a small one because it's pretty small size, even though it only takes about 25 hours to rotate on its axis. So both of those planets tend to have just two big circulation cells, as opposed to our, 6 circulation cells, 3 in each hemisphere. All right, so there are some factors, natural factors, that can cause the climate to change on the long term. So the first one is solar brightening. So the sun has gradually brightened. It's about 30% brighter now than it was when it was first born. However, the other 3 effects that I'm about to talk about easily overwhelm it. Sadly, though, I had a professor in undergrad, a physics professor, who believed that all of the climate change that we're currently seeing was caused by the sun getting brighter and the Earth receiving more energy from the sun. That's not at all correct. The current climate change we're receiving is happening on too short of a time scale for us to notice changes in the sun's brightening. So tons of other effects will overwhelm the sun's brightening, especially on a day-to-day basis, on a year-to-year basis even. The other effects are stuff like changes in the axial tilt of the planet. This will make seasons more extreme, where, for example, the extra summer warmth will prevent ice from building up, which reduces reflectivity and makes the whole planet warmer. And vice versa for a small tilt, which adds extra winter coolness, builds up ice, which increases reflectivity and makes the whole planet cooler. So Earth has pretty much just a right axial tilt, at least at the moment. There's evidence for that axial tilt to have changed over the past several tens of thousands of years. But just for the moment, it's got a pretty good axial tilt. Changes in reflectivity will also affect climate change long term. So if a planet reflects more sunlight, then the planet will cool. This can be caused by things like volcanic eruptions, fluctuating ice caps, and human activity as well. We believe that change in reflectivity is really what caused the dinosaurs to go out. The meteor obviously killed dinosaurs in the immediate impact range, and probably created a tsunami that wiped out dinosaurs living along the coasts of nearby continents. But it was all the dust, all the dirt that the meteor shot up into the atmosphere that increased the reflectivity, which made the planet much cooler, which caused plants to die out because they weren't getting enough sunlight. And once you kill off that bottom layer of the ecological food chain, then there go all the top layers too. And that's what I think killed the dinosaurs. The meteor definitely caused it, but it wasn't the direct impact of the meteor that killed the dinosaurs. And obviously, if you change the greenhouse, how much greenhouse gases are in the atmosphere, then that will really change the climate long term. And it's the most important factor since it's a feedback loop. If you increase the amount of greenhouse gases, then the planet will warm. And if the planet warms enough, then the water will continue to evaporate. Water is a greenhouse gas. So there's going to be a lot of water in the atmosphere, leading to an increase in atmospheric pressure, which will cause more water to evaporate and go on and go on. It's a feedback loop. Conversely, if the abundance of greenhouse gases decreases, then the planet will cool and atmospheric pressure may decrease as gases freeze, which will then continue to cool the planet. So changing those greenhouse gases really kind of screws everything up. Now, where did we get all of these gases in the first place? Well, there are three major sources of atmospheric gas. So the biggest one is outgassing, volcanic outgassing. So as volcanoes erupt, they are releasing trapped gases from the interior, releasing it into the atmosphere. So the most common gases that are released are water, carbon dioxide, molecular nitrogen, that's two nitrogen atoms bonded together, hydrogen sulfide, and sulfur dioxide. This happens on Venus, Earth, and Mars. And to some extent, in the early history of those planets, Mercury and the Moon as well. We also have vaporization. Vaporization is the general term for changing something into a gas. So if some of those outgassed gases condense to form liquids or ices, liquids or solids, then the vaporization of those materials could be another source of gas. So as liquids evaporate or solids sublimate into gases, that will add obviously gas to the atmosphere. And then we also have surface ejection. So micrometeorite impact, solar wind particles, and high energy photons can knock individual atoms or molecules from the surface. This has the biggest impact on the Moon and Mercury because they don't have much of an atmosphere. So all of those things can really hit the surface. Meanwhile, on Venus, Earth, and Mars, even Mars's smaller atmosphere does keep micrometeorites and solar photons and solar wind particles from reaching the surface. So that's really only a big source on the Moon and Mercury. For Venus, Earth, and Mars, outgassing is probably the biggest source of gases. Now, how do we lose those atmospheric gases? Well, the opposite of vaporization is condensation. So obviously, if we take stuff from the gas in the atmosphere and put it into liquids and solids, that's taking things out of the atmosphere. So rain, hail, snow will take gas and lock it into liquids or solids. Chemical reactions can also happen that could incorporate gas into surface metal or rock, like rust. Rust is the interaction between iron-based materials interacting with the oxygen in the air, removing oxygen from the atmosphere and creating that kind of red rust that we see. The solar wind can also strip a planet of its atmosphere. So if a world doesn't have a magnetosphere, which protects it from the sun's charged particles, then those charged particles can gradually strip an atmosphere, sweeping them into space. And then just basic thermal escape. So if we've got all this gas in the exosphere, some of those particles will have high enough velocities to reach beyond escape velocity, in which case it will just fly off into space. Now, it does depend on the planet's size, its distance, and atmospheric composition, but all of the planets, including the Earth, does have some thermal escape. Which is why none of the terrestrial planets have hydrogen or helium like the gas giants do, because they were too hot. They're small enough and warm enough for hydrogen and helium to reach escape velocity and just leave. And they may have been able to retain heavier gases released later by outgassing, which is why Venus, Mars, and Earth have the substantial atmospheres that they do today. All right, so we've talked about the general processes of atmospheres. Now let's get into the details of the objects individually. Like before, Moon and Mercury are pretty similar. They really only have extremely low density atmospheres. Um, they may have had gas produced by volcanic outgassing, but they have such small size and such weak gravity that they didn't hold on to those gases for long. They were easily swept away. And so the only ongoing source of gas is what I said before, that kind of surface ejection by micrometeorites, solar wind particles, or high energy solar photons, where they'll knock free some of those surface atoms and molecules. So those two images show the Moon and Mercury's atmospheres from observing sodium being blasted off of the surfaces of those worlds by the sun. They don't really have an atmosphere. So that's all I'm going to say about the Moon and Mercury here tonight. When it comes to the Martian atmosphere, today, Mars's atmosphere is mostly carbon dioxide, but there's a very small amount of total gas. So the greenhouse effect isn't very strong. Remember, it only warmed the planet by about 6 degrees Celsius. And that's why the very small amount gives a very low atmospheric pressure, which is why you've got to have a spacesuit on, a pressurized spacesuit, if you're going to go visit Mars. And also is usually below freezing. So there's no liquid water on the surface, and there's no oxygen in the atmosphere. So there's no ozone to protect from solar UV radiation. So not only does your spacesuit have to be pressurized, it's also got to protect you from those UV rays, which would give you skin cancer otherwise. So Mars is much harder to live on than people are making it sound nowadays. However, Mars does have seasons, and it has some pretty drastic seasons as compared to Earth, because Mars has just a slightly larger axial tilt. But the real thing is that it has a way more elliptical orbit than the Earth, which gives it more extreme variation. So at the North and South poles, carbon dioxide will condense depending on whether it's summer or winter. So carbon dioxide will condense into dry ice at the polar ice caps. And then when the summertime comes for that hemisphere, that CO2 will vaporize again and go back into the atmosphere. In fact, here's a little GIF of the ice levels varying throughout the Martian year. The black holes at the center of the images are not physical. It's just where our orbiters couldn't see. We don't have good image covering there. But you see, they vary over the course of the year, of the Martian year, almost completely disappearing in the South Pole and definitely disappearing for a while in the North Pole. Mars also has some very strong winds. This sort of cycling of CO2 into the polar ice caps and then out of the polar ice caps does create these huge planet-wide dust storms. In fact, this is what happened to the rover Opportunity. A huge dust storm, which is animated here in red, covered Opportunity, blew too much dust onto its solar panels, and that was the end. Until something comes along and blows the dust off of the solar panels. That's it for Opportunity. We can't talk to it anymore. Martian winds also can spawn dust devils, which look like miniature tornadoes. Here's one series of images from the Curiosity rover. And you can see that dust devil blowing in the background. These are different from tornadoes because the air in dust devils is heated from below by the sunlight-warmed ground. And it swirls because of the way it interacts with the winds already there. Tornadoes here on Earth descend from the clouds, but they also spin because of prevailing wind conditions. And these winds leave Mars' atmosphere very dusty, which is why if you were to be on Mars, the atmosphere would appear sort of red. It gives it kind of a yellow-brown color. Now, like I keep saying, the pressures on Mars, the atmospheric pressures on Mars are too low for there to be liquid water on the surface. The polar ice caps are made mostly of water ice, with a thin layer about a few meters thick of frozen carbon dioxide. But radar images from both the Mars Express and the Mars Reconnaissance Orbiters have found vast layers of water ice surrounding both poles. And one of our landers, the Phoenix lander, despite landing hundreds of kilometers away from the North Pole, did expose a patch of water ice with its landing rockets. You can see this image, this white part here. That is a patch of water ice right underneath the Phoenix lander. That was kind of shocking for us. However, the presence of all of that frozen water does make it conceivable that some water is present in liquid form in underground locations where it's kept warm by some latent volcanic heat. So this makes us wonder what happened to Mars. So there is geologic evidence. We showed some images last week of features that look like river deltas and eroded craters and stuff like that. So there is geologic evidence that supports the idea that Mars was probably wetter and warmer, even perhaps with some rainfall, some liquid water on the surface, before about 3 billion years ago. And to support all of that, you needed to have a thicker atmosphere with a stronger greenhouse effect. You got to warm up Mars. Mars right now is too cold. So you had to warm it up. You had to have a thicker atmosphere to keep it all there, to allow rain to fall. And it is pretty likely that Martian volcanoes produced enough CO2 to make the atmosphere about 400 times as dense as it is today, and pumped enough water in the atmosphere to fill oceans, tens or hundreds of meters deep. Perhaps that whole northern hemisphere was an ocean. So what the heck happened to Mars? Right now, the leading hypothesis suggests that Mars once had a molten convective core, which, as we talked about last week, would be able to produce a magnetic field and a protective magnetosphere. But as Mars cooled, it lost one part of that. Either its core just completely cooled or convection stopped or something like that. And so the magnetic field stopped. And so the atmospheric gases were able to be stripped by the solar wind. And then water was lost from the atmosphere by UV rays. UV ray hits a water molecule, H2O. It will split the water into a hydrogen atom and a hydroxyl molecule, an oxygen and a hydrogen together, which are very easily escapable. They'll be very easily pushed away. So this figure kind of illustrates what happened. So early Mars most likely had a protective magnetosphere, a denser atmosphere, and perhaps some liquid water. And that magnetosphere protected it from the solar rays. But now the core has stopped convecting, so it no longer drives volcanism or extensive outgassing. Some remaining gases will condense or react with the surface to be locked in those polar ice caps or underground. That thinner atmosphere reduces the greenhouse warming, and the weaker magnetosphere will allow the solar wind to strip away much of the atmosphere. So that's what our leading theory tells us about what happened to Mars. When we look at Venus, it's just so extreme. Currently, the atmospheric pressure on Venus is 90 times that of Earth's surface pressure. To experience that on Earth, you have to dive a kilometer deep into Earth's oceans, about 0.6 miles deep. Venus's atmosphere consists almost entirely of carbon dioxide with no wind and no rain. The atmosphere is very thick and the pressure is so high that it can't really create wind. And any rain that happens will evaporate long before it hits the ground. And by rain, I mean any liquid something. It's probably not water, but any liquid something will evaporate long before it hits the ground. That thick atmosphere, as I mentioned before, is so efficient at transporting heat that the surface temperature, is essentially the same everywhere. Poles or equator, night or day, it does not matter. And Venus also lacks an axial tilt. So there aren't any seasons to cause temperature variations either, or atmospheric variations. Higher in the atmosphere where it's cooler, we think some sulfuric acid will condense into droplets. That's slightly reflective, which will make Venus's clouds reflective. But it's certainly a very hellish place to be. Now, how did Venus get so hot? Well, we think it was just a natural process of outgassing. giving it tons of water and carbon dioxide. Remember, both of those are greenhouse gases. So those will get sent out into the atmosphere, and then the greenhouse effect will take over and just continually heat it up. Now, Venus doesn't have a magnetic field, so all the water is gone in the atmosphere. The UV rays, just like they did on Mars, broke water into a hydrogen atom and hydroxyl, and those escaped Venus. Now, there's no water for carbon dioxide to be dissolved into. Rain actually takes carbon dioxide out of the atmosphere. So now we just got an atmosphere full of carbon dioxide that can't go anywhere. And that is what caused Venus to suffer from a runaway greenhouse effect. You can imagine this process as if we moved Earth to Venus's orbit. So it's going to get way more intense sunlight because it's closer to the sun. And that would raise the surface temperatures by about 30 degrees Celsius. Now, those higher surface temperatures will increase evaporation in the oceans, and warmer air will hold more water vapor. Water, as I keep saying, is a greenhouse effect. So that will strengthen the greenhouse effect, which will make it even warmer, which will cause more evaporation to happen, which will strengthen the greenhouse effect. And it's this huge feedback loop. So as a result, the oceans evaporate, carbonate rocks decompose, releasing CO2, and we get something that looks like Venus. So it got its CO2 from just a normal volcanic outgassing process. But since it's so hot and it didn't have that protective magnetic field, it removed the water, which allowed CO2 to accumulate in the atmosphere, which allowed it to create a runaway greenhouse effect. So now we got to ask the question, why is Earth's atmosphere so different? Well, we can break this into four smaller questions. One, why did Earth retain most of its outgassed water, enough to clearly form oceans and lakes and rivers and ponds, while Venus and Mars lost theirs? Why does Earth have so little CO2 in its atmosphere compared to Venus, when Earth should have outgassed as much as Venus? Remember, we're about the same size as Venus, so we should have done all the same things that Venus did. Why is Earth's atmosphere composed primarily of molecular nitrogen and molecular oxygen, when those are only trace gases in the atmospheres of Venus and Mars? And why does the Earth have a UV absorbing stratosphere while Venus and Mars don't? What's going on here? Well, we've sort of already answered why the Earth has enough water. As remember, Mars, water doesn't exist on Mars because the UV light broke up the water molecules, and the rest froze underground. On Venus, the water was never able to condense as a liquid due to heat, and were also broken up by UV light and escaped. Earth was probably cool enough, however, for liquid water to exist as early as about 4.3, 4.4 billion years ago, which also explains why it has such low carbon dioxide levels. So the carbon dioxide was able to dissolve into the water, removing it from the atmosphere and locking it up either into the oceans or into the rocks. So today, there's 60 times as much carbon dioxide dissolved in the oceans as is in the atmosphere, and the rocks contain some 170,000 times as much CO2 than in the atmosphere. So that explains why the Earth has so much water and so little carbon dioxide. The nitrogen is is easy to explain. Nitrogen is the most abundant component of the atmosphere, makes up 77% of the air we breathe. And it's the third most common gas released by outgassing, behind water and CO2. And we just explained what happened to all the water and the CO2. The water condensed into the liquid oceans, and the CO2 is now locked up into the oceans or into rock. So it sort of makes sense that we have a nitrogen-rich atmosphere. That's perfectly fine. No problems there. However, oxygen is the hard one to explain, because oxygen isn't released from outgassing and is removed from the atmosphere through chemical reactions. So remember, think rust. Rust removes oxygen from the atmosphere by its interaction with iron molecules, iron compounds. So where does oxygen come from? Well, the reason Earth has so much oxygen is thanks to life. Photosynthesis is probably the key part there, that it takes in carbon dioxide and expels molecular oxygen. But since oxygen can be removed from the atmosphere, as I just said, it took probably about 1 billion years before enough molecular oxygen accumulated. And then this also explains why we have a stratosphere, because life and oxygen produces the easily UV absorbing molecule ozone, which is just 3 oxygen atoms weakly bonded together. So that's why we have oxygen in our atmosphere and ozone, because we're the only planet with life on it. Now, in order to, Earth's atmosphere, Earth's climate is pretty stable. And that's very important for the ongoing evolution of life, and hence to our relatively recent arrival as a species on this planet. Had our planet undergone a runaway greenhouse effect like Venus, life would have been extinguished. And if Earth had suffered a loss of atmosphere and a global freezing like Mars, any surviving life would have been forced to hide in underground pockets of liquid water. And Earth's climate isn't perfectly stable. We have had ice ages and warm periods, but nonetheless, even through those ice ages and warm periods, Earth's temperature has remained in a range in which some liquid water could still exist and harbor life. And so apparently, there must be some mechanism that allows Earth's climate to remain relatively stable. And that mechanism is actually the carbon dioxide cycle. So let's follow this cycle. So atmospheric carbon dioxide dissolves in rainwater, which creates a mild acid. And that mildly acidic rainfall will then erode the rock it falls upon, and rivers will carry down those broken down molecules into the oceans. In the oceans, calcium from those broken down minerals combines with dissolved carbon dioxide and falls to the ocean floor, making carbonate rocks such as limestone. And over millions of years, the conveyor belt of plate tectonics, which we talked about last week, will carry those carbonate rocks to subduction zones where they're carried downward. And as they are pushed deeper into the mantle, some of the subducted carbonate rocks melt and release their carbon dioxide, which then outgasses back into the atmosphere through volcanoes. And the whole process repeats itself. And this CO2 cycle sort of acts as a long-term thermostat for Earth, because it has sort of a built-in form of negative feedback that returns Earth's temperatures towards normal whenever it warms up or cools down. So if the Earth's atmosphere gets too cold, then it's going to rain less. There's less evaporation. So there's going to be less water falling out of the atmosphere. So there's going to be less rain to dissolve the CO2 from the atmosphere, removing it from the atmosphere. So that means CO2 is going to build up in the atmosphere, which will then strengthen the greenhouse effect and warm the Earth up. If the Earth gets too warm, then there's going to be more evaporation, causing more rain to fall. More rain will remove carbon dioxide, more carbon dioxide from the atmosphere. So the carbon dioxide concentration will build up in the oceans, removing it from the atmosphere, weakening the greenhouse effect and cooling it down. Now, clearly the Earth has still had ice ages and warm periods. So calculations have shown that the CO2 cycle does take around 100,000 years to react to large changes. So it's not going to react on the time scale of a human lifespan. It does take time for the CO2 cycle to fix whatever changes in the Earth's atmospheric temperature there are. Now that brings us to human-made climate change, because recently the temperatures have been increasing way faster than it would have through natural processes. And there's 3 kind of key facts, 3 basic facts that link global warming with human activity. So the first one is that given the observed properties of the planets that it explains, the greenhouse effect is a very well-established scientific model, which gives us no doubt that a rising concentration of greenhouse gases would make the planet warm up more than it would otherwise. Second, observations have shown that the carbon dioxide concentration in the atmosphere is 40% higher than it was before the Industrial Revolution and is continuing to rise. So here's a few plots. The top left one shows the temperature change in degrees Celsius relative to the past millennium. So you can see temperature varying quite a bit. The bottom one is the concentration of carbon dioxide in the atmosphere in parts per million as a function of time, thousands of years ago. So, and you can see that periods of higher CO2 concentration coincide with times of higher global average temperature. Now, if we look to today, whoo boy, since 1750 all the way to today, it has increased so much. It is above all peaks occurring in the past 800,000 years. So something's happening in the recent human timescale to cause CO2 in the atmosphere to increase rapidly. The third one says that climate models that ignore the effects of human activity fail to match the observed rise in global temperatures. Models that include the enhanced greenhouse effect caused by humans match the observed trend quite well. So here's another plot, the change compared to the past average global temperature in degrees Celsius on the vertical, the horizontal, the years. The black curve is the observations. This is clearly showing in recent years, since about 1950, a rise in average global temperatures. The blue curve is computer models that include only solar and volcanic changes. And you can see, especially as we get towards modern times, it doesn't at all match the black curve. But the red curve, which includes the effects of human activity, does follow the black curve and does explain the warming. These facts offer convincing evidence that humans are tinkering with the climate in a way that may cause major changes, not just in the distant future, but in our own lifetimes. The same models that convince scientists of the reality of human-induced global warming tell us that if current trends in the greenhouse gas concentration continue, that is, if we do nothing to slow our emissions of carbon dioxide and other greenhouse gases, the warming trend will continue to accelerate. So by the end of this century, the global average temperature would be 2 to 5 degrees Celsius, or about 4 to 10 degrees Fahrenheit higher than it is now, giving our children and grandchildren the warmest climate than any generation of humanity has ever experienced. What I'm about to show you, it's going to go by kind of fast. This is, if you just search up XKCD Earth's climate, it should be like the first link that you see on Google. This is going to show you how Earth's climate has changed over the past 22,000 years. Dotted lines are models, and as we get towards our time period, it will change to solid, which is from observations. In the center is 0 degrees Celsius compared to the 1961 to 1990 average. Towards the left, it's colder. All the way down left is at -5 degrees Celsius. Towards the right is warmer at +5 degrees Celsius. And we're going to start here about 20,000 BCE, where the Earth is about 4 degrees colder than during the late 20th century. And it's going to go by fast. So I just want you to watch the line move and change. You can go look this up and read all the things that it's saying as we go on. So you can see it's still relatively cold. Then it's going to start warming up soon, a little bit, very slowly. Humans are around by now. They're in North America. We've domesticated dogs. There's no more ice sheets in Chicago. Decreases a little bit, but then goes back, starts warming again. Saber-toothed tigers extinct. We're pretty warm now, just about a ½ degree Celsius warmer than the late 20th century average. Humans are starting to develop civilization, the wheel, language, settling the Fertile Crescent, Egyptians. And it's cooling a bit. Now we're at 0 degrees relative. Cooling even further, but just still hovering around 0 of the Little Ice Age. And now at the end, we've drastically warmed up. So airplanes, world wars, nuclear weapons. 2016 was present day for when this comic was released. And you can see there were 3 scenarios. I think we are still pretty much on the current path. Recent studies have shown, I think we're still on the current path. If we immediately limit emissions, we're still going to be pretty warm. And optimistically, it's still going to be very warm. So I personally don't have a lot of hope, but that doesn't mean we shouldn't try. If we don't do anything, the consequences of climate change will be widespread. So not only will there be changes in rainfall pattern, the droughts that the current Southwest of the United States is likely caused by climate change. There'll also be increased evaporation, which means stronger hurricanes and, oddly enough, winter storms. Melting polar ice won't raise sea levels because that ice is already in the ocean, but it will lead to species extinction like polar bears, which rely on ice flows to move around. That will also sort of warm the oceans. It's the melting glacial ice, the ice that's on land, that will cause the sea levels to rise. As more rain happens, there's going to be an increased levels of carbon dioxide in water, which leads to more acidic ocean, which is leading to already what we're seeing as coral reef demise. Here's a map of the current coastline of current coastline of Georgia and South Carolina. You see Savannah here at the bottom, Charleston up there at the top. That's the current coastline. If we just raise the coast by a foot, there goes Savannah, there goes Charleston. My favorite beach is Folly Beach, just outside Charleston. I can't go there anymore. If we do nothing, this will happen by 2050, according to this model, at the latest 2090. So most likely within my lifetime, certainly within the lifetimes of children being born today, if we do nothing. And even if we do something, this will still probably happen by the 2100s, 2200s. So we've already sort of screwed the pooch here. But we definitely contact your Congress people, contact the president, contact your local representatives and get them to do something about this. Because we will be dealing with the drastic effects. I mean, just in this region, that's 8 to 40,000 people that now don't have homes that we've got to deal with. So if you think the migrant crisis at the U.S.-Mexico border is disastrous, wait till we start seeing migrants caused by climate change. That's going to be even worse. So on that bright and cheery note, we will end tonight. Next week, we will talk about the Jovian planets in a little bit less detail than we've been talking about the inner planets, since they don't have a surface to talk about. So with that, if you have any questions, feel free to comment below. Direct message me. I'll be happy to answer them. I hope y'all are enjoying this, and I will see y'all next week.